Welcome to Unit 1 of AP Calculus AB, Limits and Continuity. This unit is the foundation of everything that comes after. Before we can talk about derivatives, integrals, or any of the powerful tools calculus gives us, we need to deeply understand one core idea, the limit. By the end of this video, you will understand what limits are, how to calculate them, what continuity means, and how the intermediate value theorem works. Let's begin. So what exactly is a limit? The core question a limit asks is this: as x gets closer and closer to some number, a, what value does f of x approach? Notice we are not asking what happens atx equals a. We are asking what the function is, heading toward as we get near a. We write this as the limit of f of x as x approaches a equals L. Here, x arrow means x is getting close to a, but never actually reaching it, and L is the value f of x is approaching. This distinction between approaching and arriving is absolutely fundamental to understanding calculus. One of the most important skills in calculus is reading limits from graphs. Look at this function. It looks like f of x equals x plus 1, but there is a hole at x equals 2. The function is not defined there. However, a separate filled dot sits at y equals 1, meaning f of 2 equals 1. Now watch as we approach x equals 2 from the left. As x gets closer and closer to 2, the function value gets closer and closer to 3. And approaching from the right, same thing. Both sides approach 3. So the limit of f of x as x approaches 2 equals 3, even. Though f of 2 itself equals 1, the limit and the function value are two completely different things. Sometimes the function behaves differently depending on which direction you approach from. That is where one-sided limits come in. The left-hand limit, written with a superscript minus, means we approach it from values less than a. The right-hand limit, superscript plus, means we approach from values greater than a. The crucial rule is this: the two-sided limit exists if and only if both one-sided limits exist and they are equal to each other. If the left and right limits give different values, the two-sided limit does not exist, often written as DNE does not exist. Another way to estimate limits is with a table of values. Take f of x equals x squared minus 4, all divided by x minus 2. If we try to plug in x equals 2 directly, we get 0 over 0. That is undefined. But we can build a table, plugging in values that get closer and closer to 2. From the left, 1.9 gives 3.9, 1.99 gives 3.99, 1.999 gives 3.999. From the right, 2.001 gives 4.001, 2.01 gives 4.01, 2.1 gives 4.1. Both sides are clearly approaching 4, so the limit equals 4. This table method is useful for estimating when we cannot calculate algebraically, and it builds strong intuition for what limits mean numerically. Once we understand what limits are, we need efficient rules to calculate them. These are the limit laws. The sum rule says the limit of a sum is the sum of the limits. The product rule: the limit of a product is the product of the limits. The quotient rule: the limit of a quotient is the quotient of the limits, as long as the denominator's limit is not 0. The constant multiple rule: you can pull a constant outside the limit. And the power rule: you can bring an exponent outside the limit. These laws allow us to break complicated limits into simpler pieces and evaluate them step by step. The simplest technique for evaluating limits is direct substitution. If a function is continuous at x equals a, then the limit as x approaches a is simply f of a. You just plug in. For example, the limit of x squared plus 2x minus 1 as x approaches 3 equals 3 squared plus 2 times 3 minus 1, which equals 9 plus 6 minus 1, which equals 14. The important warning: if direct substitution gives you 0 over 0, that is an indeterminate form. It does not mean the limit is 0 or undefined. It means you need a different technique, usually factoring. When direct substitution gives 0 over 0, the most common fix is factoring. Take the limit of x squared minus 4 over x minus 2 as x approaches 2. Plugging in 2 gives 0 over 0, indeterminate. Step 2, factor the numerator. X squared minus 4 is a difference of squares, so it factors as x minus 2 times x plus 2. Step 3, cancel the common factor. Since x is approaching 2, but never equals 2, x minus 2 is never actually 0, so we are allowed to cancel it. We are left with the limit of x plus 2 as x approaches 2. Step 4, direct substitution.
2 plus 2 equals 4. That is the answer. Other techniques include multiplying by a conjugate, useful with square roots, and using trigonometric identities. What happens to a function as x grows without bound? As x approaches positive or negative infinity. Look at this curve. As x gets larger and larger, the function value gets closer and closer to 3. We write the limit of f of x is x approaches infinity equals 3. When this happens, the line equals 3 is called a horizontal asymptote. The key tool here is the fact that 1 over x to the n approaches 0 as x approaches infinity for any positive n. Intuitively, as x gets enormous, any constant divided by that enormous number becomes negligible. It shrinks to 0. For rational functions, polynomials divided by polynomials, there is a clean pattern for limits at infinity. The trick is to divide every term by the highest power of x in the denominator, then use the fact that 1 over x to the n goes to 0. Case 1. If the numerator and denominator have the same degree, the limit is the ratio of their leading coefficients. Case 2. If the numerator has lower degree, the limit is 0. Case 3. If the numerator has higher degree, the limit is positive or negative infinity. No finite horizontal asymptote. These 3 cases are worth memorizing cold. They appear constantly on the AP exam. Now what about limits where the function blows up? Take f of x equals 1 over x. As x approaches 0 from the right, 1 over x grows without bound. It approaches positive infinity. From the left, it approaches negative infinity. Since the two one-sided limits are different, the two-sided limit does not exist. But more importantly, the line x equals 0 is a vertical asymptote. Vertical asymptotes occur where the denominator of a rational function equals 0, provided the numerator does not also equal 0 there. Always check both sides. The function might go to positive infinity from one side and negative from the other. The squeeze theorem, sometimes called the sandwich theorem, is a powerful tool for limits that are hard to compute directly. If g of x is less than or equal to f of x, which is less than or equal to h of x near x equals a, and if both g and h approach the same limit L as x approaches a, then f must also approach L. It is squeezed between them. The classic example is f of x equals x times sine of 1 over x near x equals 0. The sine function oscillates wildly. We cannot just substitute, but we know the absolute value of x times sine of 1 over x is at most the absolute value of x, so we squeeze it between negative x and x. Both approach 0, so the limit is 0. Now we are ready to define continuity precisely. A function. F is continuous at x equals a if 3 conditions all hold. First, f of a exists. The function is actually defined at that point. Second, the limit of f of x as x approaches a exists. Both one-sided limits agree. Third, the limit equals f of a. The function value matches what the limit is approaching. Think of it informally as you can draw the graph through x equals a without lifting your pencil. If any one of the 3 conditions fails, the function is discontinuous at a. There are 3 main types of discontinuity. A removable discontinuity, also called a hole, occurs when the limit exists, but either the function is not defined there or it has the wrong value. You could fix it by redefining f at that single point. A jump discontinuity occurs when the left hand and right hand limits both exist but are not equal. The graph jumps from one value to another. An infinite discontinuity occurs when the function heads to positive or negative infinity near the point. This is what happens at a vertical asymptote. Understanding these types helps when deciding if a function can be made continuous by redefining it at a point. A function is continuous on an open interval if it is continuous at every single point inside that interval. For a closed interval at b, we also require continuity from the right at a and from the left at b. The good news is that most familiar functions are continuous everywhere on their domains. Polynomials are continuous everywhere. Rational functions are continuous everywhere, except where the denominator is 0. Sine, cosine, exponential, and logarithmic functions are all continuous on their natural domains. Compositions and arithmetic. Combinations of continuous functions are also continuous. So in practice, mainly watch out for rational functions, absolute value functions, and piecewise defined functions. The intermediate value theorem is one of the first major theorems of the course. If f is continuous on the closed interval ab and k is any value strictly between f of a and f of b, then there must exist at least one value c in the open interval ab such that f of c equals k. In plain English, a continuous function cannot skip over values. If it starts at one height and ends at another, it must pass through every height in between. Visually, draw the horizontal line equals k between the two endpoint values. A continuous curve must cross it, somewhere. The theorem guarantees existence. It does not. Tell us how many crossings there are, or where exactly. Let us apply the intermediate value theorem to a concrete problem. Show that f of x equals x cubed minus x minus 1 has a root on the interval from 1 to 2. First, compute the endpoint values. F of 1 equals 1 minus 1 minus 1 equals negative 1, less than 0. F of 2 equals 8 minus 2 minus 1 equals 5, greater than 0. Second, note that f is a polynomial, so it is continuous everywhere, in particular on the closed interval 1 to 2. Third, apply the IVT. Since f of 1 is negative and f of 2 is positive, 0 is between these values. Therefore there must exist some c in the open interval 1 to 2 where f of c equals 0. That is a root. The IVT gives us existence without finding the exact value. A powerful idea. Two special trigonometric limits come up constantly in calculus, especially when deriving the derivative of sine and cosine. The first, the limit of sine x over x as x approaches 0 equals 1. This is not obvious. If you plug in 0, you get 0 over 0. But using the squeeze theorem and some geometry, we can prove it rigorously. The second, the limit of 1 minus cosine x over x as x approaches 0 equals 0. These two limits are the gateway to all of trigonometric differentiation. On the AP exam, you will use them directly and in combination with limit laws. Memorize them and understand them deeply. Let us pull everything together. Unit 1 gave us the language of calculus. Limits ask what a function approaches, not what it equals. One-sided limits let us analyze functions that behave differently from left and right. The limit laws let us break complex limits into simple ones. Algebraic techniques, factoring, conjugates, trig identities, resolve indeterminate forms. Limits at infinity describe end behavior and horizontal asymptotes. Vertical asymptotes arise where the function blows up. The squeeze theorem handles oscillating or complicated functions. Continuity requires 3 conditions and comes in 3 flavors of failure, and the intermediate value. Theorem guarantees that continuous functions hit every intermediate value. This is your toolkit. Master it, and Unit 2, derivatives, will make complete sense. That wraps up Unit 1 of AP Calculus AB. You have covered everything from the basic definition of a limit all the way to the intermediate value theorem. Coming up in Unit 2, we will use limits to build the derivative, the central tool of differential calculus. If this video helped you, subscribe so you do not miss Unit 2. Good luck with your studies.